Good afternoon, class. We are looking at Chapter 3 Derivatives, Section 3.4, the product and quotient rules. So we looked at derivatives using definitions in the first two sections. Then we looked at some basic differentiation formulas, and we're going to continue with the product and quotient rules. Again, a quick reminder, we started with the slope of a secant line, having two lines and representing them in different manners. All of them represent the slope of a line given 2 points. And the lines in blue are secant lines. The line in red is a tangent line. As Q moves towards P, it approaches the tangent line. And we ended up with the limit of all of this, and depending upon which one you use, for example, this one would be the limit of f of x minus f of a over x minus a as x approaches a, and the rest of them, and we call that f prime of a. Using the equation of a line in different formats, we used specifically the point slope, and the equation of a tangent line is achieved. And in general, the definition says f prime of x is the limit of f of x plus h minus f of x over h as h approaches you. So we have the definition, we have some basics, and these are the basics we learned in the previous section. The derivative of a constant is 0. This is the power rule. The derivative of x to the power of n is n x to the power of n minus 1. The derivative of kx is k, where k is a constant. The derivative of e to the power of x is itself. The derivative of sine is cosine. Cosine is negative sine. And the rest of them, we will elaborate on them today. So we are adding two more, the product and the quotient rule. And what I want you to look at when I use this shorthand notation, f represents f of x, g represents g of x. So f g prime, that means take the derivative of the product, which is f prime g plus g prime f. And f over g prime is f prime of g minus g prime of g prime f over g squared. Now, some of you have already seen this formula, slightly in a different order. The order that they use is f of x g prime plus g of x f prime. The reason I'm using this one, because it makes it easier to memorize the quotient rule. Ultimately, it is up to you. If you have learned it and you want to use the way you have already learned it, more power to you. All right. Couple of things I want to mention here. One of them is what we learned previously as far as the sum and difference rules are concerned. So by analogy, one may be under the assumption that according to the sum and the difference rules, one may be tempted to guess that the derivative of a product is the product of the derivatives. So that's not the case, and I have the proof of both the product rule and the quotient rule at the end. You're not responsible for it, and there's not enough time to go over that. But what I'm going to cover is this. If we look at an example, we see that this is not working. So we can see, however, that this guess is wrong by looking at a particular example. A simple case. If we choose f of x to be x and g of x to be x squared, then the derivative of the first one is 1, the second one is a 2x, simply by using the power. Very straightforward. If we multiply these two, f of x times g of x, we get x cubed, and again by the power rule, we can find the derivative, or fg prime, to be 3x squared. So if we go with f prime g prime, that means we're going to multiply 1 and 2x. Their product is 2x, and clearly that's not the answer. Therefore, f g prime is not f prime g prime. So the derivative of the product is not the product of the derivatives. However, with the shorthand notation, I said fg prime is f prime g plus g prime f. Therefore, f prime times g, if I multiply these two, I get 1 times x squared plus g prime f. If I multiply these two, I get 2x squared, and as you can see, they add up to 3x squared, and that's exactly what we got here. Before we move on to examples, I'd like you to try this at home, and when I say find the derivative both ways, one of them obviously using the rules of this section, the product rule. One of them, you distribute first. You use your algebraic techniques to distribute, and you can use the power rule. So I like you to do that. I like you to do that at home to see that they give you the same result. We are going to go with a warm-up example for this product rule, and the reason I don't want to simplify, differentiate, do not simplify, because I want to emphasize there is one step of calculus. There are several steps of algebra. You need to finish it at home. We will look at examples that we will finish from A to Z, but for this one, I'm going to call the first parenthesis the f function, the second one the g function, and I'm going to stick with the simplified formula fg prime is f prime g plus g prime f. So first and foremost, I need f prime. Can anybody tell me what is f prime? By the power rule, this is 4x cubed minus 6x squared. So this is f prime times g, just times the parentheses in blue, 3x squared minus 5x, plus g prime. What is g prime, class?
It's like 5.
Say it again, please.
Exact minus 5.
Beautiful. According to the power rule, this becomes 6x, this becomes minus 5, times f, the f function, the red function, put it just next to it. As you can see, this is not finished. You distribute and you finish the job. But again, I just want to emphasize the concept of a product rule. If f of x is x times e to the power of x, we want to find f prime and f double prime. You remember the higher powers, okay, higher derivatives, if you will. I'm going to put a raised dot in between to make sure everybody can see. This requires the product rule, and I'm going to call this f and this g. If you want, you can change this to y if you want. It doesn't matter. So I'm going to use the product rule on that. Here's fx, so f prime is 1. So you memorize these formulas. So when you come across this, you write the product rule from your memory and you start working on it. So the derivative of x is 1, then times g, the g function is simply e to the power of x, plus g prime, the derivative of e to the power of x is itself, plus e to the power of x, and times f, which is the x. And I can factor the e to the power of x out, and I write 1 plus x, x plus 1, doesn't matter. If I want to differentiate this again. I'm going to call this one the f function and the whole parenthesis the g function. And I'm going to use the product rule again. So f double prime, I need the derivative of e to the power of x. That would be f prime. So that's itself. So e to the power of x. And then I'm going to multiply it by the parentheses. 1 plus x, x plus 1 doesn't matter. Plus g prime, the derivative of the parentheses is simply 1 and times e to the power of x. And there you have it. And all we have to do is simplify. To do so, I'm going to do the factoring, everybody. Which means if I take e to the power of x out, I get x plus 1 from the first, 1 from the second, and I get e to the power of x times x plus 2. I think it's pretty straightforward, everybody. Again, I need to put a raised dot here to emphasize this requires a product rule as well. And let's say this is the f function and sine is the g function. Again, I'm going to stick with the product rule, everybody. F x squared gives me f prime 2x times g, just times sine x, plus g prime, the g function is sine x, its derivative is cosine x, times f, so times x squared. Practically, we're done. You really have to put the x squared in front because I don't want anybody to be under the assumption this is x cubed. So you just move the x squared to the front and we are done. We need to use the quotient rule in this case. And again, I don't want to simplify, go through the algebraic steps. Here's the shorthand notation, and I hope you realize when I did the product rule, I had the product of these two pieces. So the same thing, you put a negative in between in essence. So y prime, and I'm going to call this f over g, so f over g again. So I need f prime, which means I need the derivative of the numerator. As you recall, it's 4x cubed minus 6x squared. I'm going to simply multiply it by the g function, the denominator, the blue function. So I put the blue function next to it in a parentheses. Minus g prime, the derivative of the bottom is 6x minus 5. And next to it goes f, the top function, put next to it, over g squared, just the bottom function, put it in a parentheses and square it. So g squared means put the bottom function and square it. Again, this is not done. There are several algebraic steps to finish the job, but the reason I want to stop here, I want to emphasize the importance of the calculus step, and the rest is algebra that you've seen. Please finish that at home. Now we are going to differentiate this, and we are going to finish from A to Z. Again, and notice that you have to use the quotient rule. We are going to call this f over g. The f function is the numerator, x squared minus 3x. The g function is the bottom, which is x minus 1. And we are going to use the quotient rule here. So big fraction bar, and we need f prime. The derivative of the numerator is clearly 2x minus 3. Next to it goes g, the bottom function. You just put it in a parenthesis next to it. In other words, multiply by that. Minus g prime. The derivative of the bottom is just 1, number 1, because it's x here. Or you can think of it as 1x, and this is a constant which gives you 0. And times f. F is the top function, x squared minus 3x, so multiplied by that. As far as the bottom, just write this in a parenthesis and square it. And again, this is the only calculus step, everybody. Let me put the asterisk next to it. And you're done with calculus. Now we are going to do algebra. So 2x and x, the product is 2x. And negative 3 and negative 1 is plus 3. The middle term, again, I remind you how you did that in elementary algebra. You would say this is negative 2x. This is negative 3x, and you would add them up. Negative 3x and negative 2x is negative 5x. The first one 2x squared, the last one plus 3, and this one is minus x squared plus 3x. So I'm assuming we can do the FOIL fairly fast. Now I want to simplify this, and I can combine 2x squared and negative x squared into x squared. I can combine minus 5x and 3x to negative 2x. Now, anytime you have a fraction or a fractional expression or a rational expression, you must put it in its lowest term. In other words, is there a common factor between the numerator and the denominator? And to do so, you have to see if you can factor the top, and more importantly, if you can factor it, does it have a factor of x minus 1? Because even if you can factor, but it doesn't have a factor of x minus 1, that means we can't simplify. So what I want to remind you of the quadratic equation. Ax squared plus bx plus c equal to 0. X is minus b plus minus the square root of b squared minus 4ac over 2a. Everybody remembers that. What's underneath is called the discriminant. When it's positive, gives us two real solutions, two distinct solution. If the solution will be rational if the discriminant is a perfect square, and irrational otherwise. If it's 0, has one real solution, and if it's negative, has no real solutions or two complex solutions. Furthermore, in this concept where it says a perfect square, that means if b squared minus 4ac is a perfect square number, then ax squared plus bx plus c can be factored. Otherwise, it cannot be factored. Now, can we factor this expression? All you have to do, evaluate b squared minus 4ac So I'm going to write here a is 1. We're looking at the top. B is negative 2. C is 3. So b squared minus 4ac is negative 2 squared minus 4 times a, which is 1, times c, which is 3, and that is minus 8. Not only it's not a perfect square, it's just negative. That means there's no way to factor it. In fact, if you were to solve it, it would have two imaginary solutions. So again, what you have here, just a reminder of what you've seen in elementary algebra. Let's move on. We are going to differentiate the square root of x times e to the power of x. And to do so, we are going to change square root of x to x to the power of 1/2, because that's why I put this to remind you of some of the properties. So square root of x is x to the power of 1/2. And the reason we do it, so we can use the power rule on that. Let me put a raised dot again in between. That is extremely important. So we understand that we require the product rule on this. So I'm going to call this f times g. Here's the f function, x to the power of 1/2. Here's the g function, e to the power of x. We are going to use the product rule. I need f prime, which is 1/2. Remember, 1/2 becomes the coefficient. X to the power of 1/2 minus 1, which is 1/2 x to the power of negative 1/2. So I assume everybody remembers the power rule, knows how to use it. So times g, so times e to the power of x. Plus g prime, well, e to the power of x, the derivative is itself, plus e to the power of x, and then times f. F is x to the power of 1/2, or back to square root of x. First and foremost, this one, remember the negative exponential rules. Basically, you move them. If it's negative, take it down, make it positive. Up here, if it's negative down here, bring it up, make it positive. So I'm going to move this down, becomes x to the power of positive 1/2, or square root of x. Now, we normally want to combine them in a manner that we could solve them if we set it equal to 0. There are a couple of ways. One way is just to find the LCD and use a huge fraction bar and add them up. The other one is that we know that 2 square root of x is, if you were to combine them, as the LCD. And so this one has it, this one doesn't. So raise it by a factor of 2 square root of x over 2 square root of x. And I hope you realize, oh, this one we're going to write it. This one, e to the power, by the way, e to the power of x, you can write it at top. Again, I want to make sure everybody understands. If you wrote this as e to the power of x over 2 square root of x, it is absolutely the same thing. You don't have to worry about that. Same thing here, e to the power of x over 2 square root of x is exactly this one. But what is the product of these two? I hope you recognize the product of square root of x and 2 square root of x is 2x, and therefore we have the following. Okay, so that's why I put them in different colors. You recognize this is the same as this one or this one. So if I factor this out, this gives me 1, this gives me 2x, and we write it as 1 plus 2x. Again, very straightforward, everybody. I hope everybody is okay with that, not a big deal. All right, let's move on. And in this example, clearly we are going to use the quotient rule. So let me call this f over g. We're going to use this. So we need f prime, the derivative of the top is simply itself, e to the power of x. We're going to multiply it by g, meaning multiplied by the denominator. Just write the parentheses and 1 plus x. Minus g prime, the derivative of the bottom, I hope you recognize it's just 1 because this is 0, this is 1. And multiplied by f, the top function, just write it. And the next step is just to write the bottom, g, and put it in a parentheses, square it. Done with calculus. This is the only calculus step, and we are done. As this was the only calculus step, and the rest of them were all algebra. So we are going to distribute e to the power of x, e to the power of x times x, minus e to the power of x. And notice I can cancel out these two. This is the only thing left in the numerator, and you must bring the x in front. Otherwise, it's awkward. We're going to continue with more examples. Y is 1 plus sine x over x plus cosine x. Clearly, we are going to use the quotient rule again. I would write the quotient rule. As soon as I see this question, I would write the quotient rule from my memory, and I'm going to apply that. Therefore, I'm going to call this f over g. So I need, first and foremost, f prime. What is the derivative of the top? This is 0, and this gives you cosine x. The derivative of sine is cosine x. So I'm going to multiply it by g. Simply put this in the parentheses. The bottom goes inside this parentheses because that's the g function. Minus the next thing, I need the g prime. So x gives me 1 plus cosine x gives me minus sine x, because the derivative of cosine is negative sine. And I need to put the f, the top function, next to it. Then all you have to do, g squared, meaning write this in a parentheses, write the bottom in a parentheses, and square it. And again, class, let me put an asterisk next to it. Done with calculus. Now we're going to use our algebraic techniques. Notice the top is, this one is a minus b. The second part, it's times a plus b, the conjugates. And their product is a squared minus b squared. So that this part becomes 1 minus sine squared. What about this part? Distribute. We put the x in front, x cosine x plus cosine squared, and we said this is 1 minus sine squared. Now, I'm going to remind you of Pythagorean identities in trigonometry. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. And 1 plus cotangent squared equals cosecant squared. So everything we come across, I remind you. But I hope it comes back to you. I hope you memorize to work on it, to memorize and remember them for the exam. And so if sine squared plus cosine squared is 1, that means sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. So this is just cosine squared. So we're going to replace this with cosine squared, everybody. We can cancel out x squared and negative cosine x squared. So the numerator has only x cosine x, and the denominator, you just write it, and we are done. That's the final answer, everybody. G of t is t minus square root of t over t to the power of 1/3, and I'm asking, do we need to use the quotient rule? What I want to mention is that there are times that we need to use the quotient rule, everybody. And if you avoid it, normally you make a mistake. Not all the time, but normally. So my suggestion is learn the quotient rule and use it whenever you need it. However, if we don't need to use it and we use that, we make it more difficult. So do we need to use the quotient rule? No. This is one fraction, this is one fraction, because the denominator has one piece. I don't want to say necessarily a term because it's not a polynomial of degree of one term. So this is one, and this is the second fraction. And of course, square root of t, just like square root of x, is x to the power of 1/2. This is t to the power of 1/2, and we use it in this fashion for the sake of the next step. That means we are going to use a quotient rule for exponentials to simplify. Notice this is the algebraic step. So we're going to use this for another algebraic step, and the exponent for t is 1 when we don't write it. So this becomes t to the power of 1 minus 1/3. This becomes t to the power of 1/2 minus 1/3. And of course, 1 minus 1/3, everybody knows, is 2/3. 1/2 and 1/3, the common denominator is 6. So 1/2 minus 1/3 becomes 1/6. And now we can use the power. So this one would be 2/3 t to the power of 2/3 minus 1, which is negative 1/3, minus 1/6 t to the power of 1/6 minus 1, which makes it minus 5/6. In other words, what I'm saying is this is 2/3 minus 1. This one is 1/6 minus 1. And the negative exponent, you just move it, take it down. As I mentioned, if you look at these two, it says if you have a negative exponent, just move it. So I'm going to move this down, becomes t to the power of positive 1/3. And this, I'm going to move it down, t to the power of positive 5/6. All right, we want to prove the derivative of tan x is secant squared. And I remind you the derivative of sine is cosine. And this requires trigonometry, algebra, and geometry to be proved. Derivative of cosine x is minus sine x. We can use that. The rest of it, the derivative of tan x is secant squared x. The derivative of cotangent x is minus cosecant squared x. The derivative of secant x is secant x times tan x, and the derivative of cosecant x is minus cosecant x cotangent x. They're all trigonometric functions, and the rest of them, we can use basically the quotient rule by writing, for example, tan x is sine over cosine, and I'm going to remind you of some trigonometric identities again. Tan x is sine over cosine, or 1 over cotangent. Cotangent x is cosine x over sine x, or 1 over tan x. Secant x is 1 over cosine x. Cosecant x is 1 over sine x. So in the case of a tangent, we're going to use this one, and we write it as sine x over cosine x, and we're going to use the quotient rule. So we are going to use the quotient rule on that, and we're going to write this as f function over the g function, everybody. All right. So we need f prime. We need f prime. So we need the derivative of sine, which is cosine, times g. So times g, cosine x. Minus, we need g prime. The derivative of cosine is negative sine. So minus sine x times f sine x. Now write the bottom, cosine x, and square it. And again, done with calculus. All we have to do, use our techniques, algebraic techniques, trigonometric techniques to finish the job. This is cosine squared. This is plus sine squared. As you know, sine squared plus cosine squared is 1, and it's a commutative property. All you have to change them. It doesn't make any difference. 1 over cosine squared. You know that 1 over cosine is secant x. Therefore, 1 over cosine squared must be secant squared x. And that's the proof. What about y equals secant x? We have the derivative as secant x or secant x times tan x. So let's get there by a proof using the fact that secant x is 1 over cosine x. And again, I'm going to call it f over g. And I'm going to use the good old quotient rule. So f prime, the top is a number. F prime is 0 times g. Just put the bottom, cosine x. Minus g prime, the derivative of cosine is negative sine, or you can refer to that if you have to, Steve, times f, the f is 1, and then put the bottom cosine x and square it. So what do we have? This is 0. This is plus sine x, or simply sine x. We can cut this into the following two fractions, 1 over cosine and sine over cosine. Please understand, if you multiply, you get this one back. So what is 1 over cosine? Secant x. What is sine over cosine? Tangent x. So we proved the derivative of secant x is secant x tan x. I highly recommend you do the other two, you prove it, and if you could prove it, it will help you with the concept. It makes it really nice and easy to use the quotient rule and understanding trigonometric functions as well. We want to find the equation of a tangent line. In this case, the function y equals x over 2x minus 7. And we want to find the equation of a tangent line at the pair 3 comma negative 3. So we need two things in order to find the equation of a tangent line. We need a pair which is given. We also need to find the slope, which means we are going to differentiate this. And to differentiate this, we are going to use clearly the quotient rule. So we are going to call this f over g. So we need f prime, which is simply 1 times g, which is 2x minus 7, minus g prime, which is just 2, right? 2x minus 7, 2 minus 0, so 2, times f, which is x, and we write the bottom in a parenthesis and square. So all we need to do is simplify by distributing here. 2x minus 7 minus 2x, and we have negative 7 in the numerator remaining. This is the derivative function. This is not the slope. It becomes the slope when you pick a x coordinate and plug it in. Because the pair takes place at 3, negative 3, we plug in number 3. That would be the slope. Now, if I plug in number 3 here, I get minus 7 over 2 times 3, 6 minus 7, minus 1 squared. So simply put minus 7 over positive 1, it's minus 7. And so y minus y1 equals m times x minus x of 1. Y minus negative 3 makes it plus 3. M minus 7, x minus x of 1, that means x minus 3. And here's the final answer. Again, just the intermediate step quickly. This would be minus 7x plus 21. You move this, you make it negative 3. And this is what you get. Again, reminding you this pair belongs to the original function. Also, it's a point of tangency belong to this. If you plug in 3, you do get negative 3, which means this process is right. It doesn't mean anything about m, whether it's right or not. This process is done properly. We want to differentiate this, and the purpose of that is to show, even if you use a different variable such as m that normally we don't use, the process is the same. Okay. So let's give everybody a moment to do this on their own. I'm going to pause the recording. All right, so we are going to go with the quotient rule. We're going to call this again f over g. So we need f prime, which is simply 9. We're going to multiply it by g. The bottom is 5m plus 4 minus, we need g prime. The derivative of the bottom is just 5. And then times the top, which is 9m minus 7. And we just put the bottom in a parenthesis and a square. That's all there is to it. The next step is all algebra. So 45m plus 36 minus 45m plus 35. So we get 71 in the numerator. The bottom is 5m plus 4 quantity squared. And we are done. We want to find an equation of a tangent line. We need a pair which is given. We need to find the slope. y equals e to the power of x times cosine x, which means I'm going to differentiate and I need to use the product rule. So I'm going to call this the f function, e to the power of x, and the g function is cosine x. Therefore, f prime is itself, e to the power of x, times g cosine x, plus g prime. The derivative of cosine is negative sine x, so plus negative sine x, and then times the other function f, which is e to the power of x. I can factor out e to the power of x. When I do that, this gives me cosine, this gives me minus sine. In order to find the slope, we have to plug in x equals to the x coordinate of the pair, namely 0. So m is y prime of 0. So if I plug in I get e to the power of 0, cosine of 0, minus sine of 0. That is 1 times 1 minus 0, which makes it 1. Very straightforward, everybody. Now, I'm going to use y equals mx plus b because this is the y-intercept and the b equals 1. 0 and a number, that means the y-intercept. It happened that m and b are both 1, so y equals x plus 1 is the equation of a tangent line. Let's differentiate again, and we are dealing with trigonometric functions. We are going to use the quotient rule. I'm going to call the top function f and the bottom function is g, and now we are going to use this quotient rule. F prime is 1 minus f is 1 minus secant x. So f prime 1 gives you 0 minus the derivative of a secant is secant tangent. The derivative of secant is secant x tangent x. And the reason is negative because we carry the same sign, okay? Times g, the bottom one, times tan x, minus g prime, the derivative of tan x is secant squared, minus secant squared. Now times f, the top, just write it next to it. And then put the bottom here, tan x, and square it, tan squared x, that's g squared. Again, I'll put an asterisk next to it, meaning we're done with calculus. Now we are going to apply our algebraic techniques, trigonometric identities, you name it. So this becomes minus secant x times tan squared minus secant squared x by the distributive property plus secant cube. The denominator doesn't change. Everything in the numerator has a common factor of secant x. So if I take the secant out, this gives me minus tan squared. This gives me minus secant x. This gives me plus secant squared x. You may notice a Pythagorean identity in trigonometry, 1 plus tan squared is secant squared. So any variation, for example, if I move the tan squared to the right, then I have this one. This is a variation of that. And we notice it's secant squared minus tan squared. So if you look at this piece, And in this piece, exactly what we have here is 1. We replace the two pieces with number 1. Can't get simplified any further. So that's the final answer. Therefore, we need to remember the differentiation formulas. The formula for the derivative of x is 1. If you multiply a function by c, a multiplier can come out. The derivative of the sum and differences are sum and difference of the derivatives. Then we have those formulas. The derivative of c is 0, x to the power of n is n, x to the power of n minus 1, and the rest of them. Many formulas you see here. We also added the product rule. Fg prime is f prime g plus g prime f, and f over g prime is f prime g minus g prime f over g squared. You need to be very comfortable with these formulas to move on, everybody.